Hi everyone and welcome to today's video on continuous random variables. Yes, we have left behind discrete random variables, bye-bye, and we are now on to continuous random variables. And you're going to say, what? We're saying goodbye to discrete already? Absolutely, I should, Coco, because not everything in life is about whole numbers. We like real numbers too. We love a bit of real. So as I say here behind me, by the end of this particular video, we want to know what a continuous random variable is, what a probability density function is, although we sort of met that before. Know the importance of probability density functions. They're really important. Big thumbs up. Understand what it means to have a probability density function with an unbounded domain. Now, again, this all gets a bit tricky later on. And understand how we can use conditional probability. Now, all of these are in previous videos. And if you haven't already seen them, there's an example of one coming up over there. But the point of it is, the maths we use is very, very similar. Expectation, variance, standard deviation. All we need to do is just make sure we know the difference about when to use it for discrete and when to use it for continuous. So what is a continuous random variable? Well, while discrete was for countable values, continuous variables or random variables can take any value at all. I just said real numbers. Now, examples, as I say here, are height, weight, and time. These can all be measured to a fraction of a second or a kilogram or a centimeter. Now that limit is only by the tool we use to measure it. So for example, when you watch the Olympics or people doing sort of athletics, you know, you'll see them get measured to some of the craziest decimal places of accuracy. Now the point of it is it important to me to know that someone's run at a speed of, 94.368729 meters per second? No. Is it important for me to know that they actually ran the race in, 1 minute, 36.9327493628700046? I could go on, but I won't. Decimal places? No, because it has absolutely no meaning in that context. But in other situations, so for example, when we do search results using Google, it comes back with, the speed, or it used to, I don't know if it still does, about the speed that it actually created the search for you. And that was down in milliseconds. Now, what we need to realize here is the point that I'm trying to get to a point in a moment, that a continuous random variable has, if I'm trying to find a specific probability of a specific event for a continuous random variable, it is 0. Now just park that for a second and hold it. So let's just say if I weighed 85 kilos, and I wish I weighed 85 kilos, it's more like 185 kilos, but you can't see what's below my chest, which is good. Then, to be fair, if I'm standing on a set of scales and it says 85 kilos, then the chances are that I probably weigh somewhere between 84.5 and 85.5 kilos, because there has been some rounding that's taken place. So 84.5, that 0.5, generally speaking, we would round up. 85.5. Now, I know you say that would round up, but that's the outside limit. That's pretty much where we're going to weigh. If my scales told me I was 85.2 kilos, then what we're looking at is, well, in this situation, it's rounded it to 85.2. So I could have actually taken away anywhere between 85.15 and 85.25, because both of those would round down or has a central value of 85.2. And finally, 85.25 would go 85.245, 85.255, and it could go on down and down and down. And theoretically, this could never stop. I could actually make my divisions smaller and smaller and smaller, and in the middle of that would appear my actual weight. So I found this little thing on Stack Exchange, which is a great little site for sort of maths knowledge. A lot of geeky people there, but thumbs up to Stack Exchange as well. Someone actually said, how do you understand why a continuous random variable is 0? Now, what I need you to realize is, go back to that weight example. I can keep measuring down to infinitesimally small sections, and that's the hint here, infinitesimally small. A continuous random variable can realize an infinite count of real numbers within its support. See, you know that a maths teacher or somebody's written this, is there an infinitude of points in a line segment. Now, what it's basically saying is, if I draw a line segment, that line segment is actually made up of an infinitesimal number of points. Now, the smaller I go, it's still there and still there and still. I can measure smaller and smaller and smaller and smaller. So, If we have an infinitude of values whose sum of probabilities must equal 1, and I'm rushing ahead, but I'll explain this in a moment, thus these probabilities must each be infinitesimally small. And the next best thing to that is actually being 0. All right, so they are almost surely equal to 0. And I think actually that's the best description here, because my mind fritzes. How on earth can I have the probability of one specific value being 0? It just doesn't make sense. But what we're trying to say is, later on, as I do this little section now, you'll find out that the divisions get smaller and smaller and smaller and are practically infinitesimally small. So, if I was to try and find the probability of me being 83 kilos, we would generally have to do some sort of a survey. We would find the probabilities of all people having weights between 83.5 and 84.5. And if we look at this diagram here, which has come from the Cambridge Essentials textbook, and it's a freaking awesome diagram, obviously some sort of survey has been done of people of all sorts of weights. And we've ended up with this sort of bell curve. And what they're trying to say is that this section here will contain the weights of 83 kilos. But because we have to take in these limits of accuracy between 82.5 and 83.5, we now actually end up with a load of rectangles. Each of these will actually stand, each of these rectangles will stand for a group of weights between some sort of limits of accuracy. So how would I now find the probability of me being 83 kilos? Well, the great thing is, because we've done a previous letter, we can use areas to define probabilities. If I actually were able to find the total area of all of these rectangles here, then I can find the area of just my rectangle and divide it by the total area. That would give me the probability that my weight falls somewhere between 82.5 and 83.5. Now notice the including and not including signs, yes? Because again, that 83.5 would theoretically be included in the next bound. So we have to be a little bit careful here, but in a moment, you will see that again, the signs change. So just to go back, if I wanted to find the probability that I was in this section here, that my weight was, when rounded, 83 kilos, I would find the area of that one section and divide it by the total area. Now imagine we were to continue doing this for a massive number of people. And you could argue an infinite number of people. Now, what would then happen is, assuming I could measure more and more accurately, my class widths, these widths here, would get smaller and smaller and smaller. And what we would notice is, so would the width of my rectangles, to the point that way would become so infinitesimally small that it actually starts to create this red bell curve here. Okay, it would follow that shape. And ladies and gentlemen, that is what's called a probability density function. All right, it is the ability to find the areas under a distribution, some sort of curve that describes probabilities. Now we've already met integration, and we can find areas under the curve. So this is all sort of leading to this in a moment. And in fact, not even in a moment now. Look at this. So with so much data, we don't need to worry about finding individual rectangles and working all those out and doing all that stuff. We can use integration. So using the general idea that we have here, we can say that the probability of my weight falling between 82.5 and 83.5 would be the integral between 82.5 and 83.5 of FW times by DW. Now you can say, what's FW? It would be this here. This would be able to be described by some sort of formula, which would be given in terms of W, right? So weight by a function of weight. Well, this stuff is freaking awesome. So the important thing about all of this is that when you want to find the probabilities of a continuous random variable, you are going to integrate, integrate, and integrate. That's literally it. So because we're dealing with probabilities though, what does that suggest the area under my graph would have to be? Well, hopefully, if you've read above, then the point of this is, because we're dealing with probabilities, you cannot have a total probability of 1.7. Doesn't make any sense. You can't have a negative probability. Doesn't make sense. So what we know is, for this to be a probability density function, i.e. the graph talks about probabilities as a sum of all of my probabilities, then the area under that graph cannot be anything other than 1. Right? It must equal 1. There are questions on the exam that tell you this or trick you with this all the time. So hopefully it makes sense. And this is a more formal description of how to find probabilities. Now, the probability that falls between A and B of some continuous random variable x, and notice we're using x again, is the integral between a and b of the function of x. Really important. The values of f of x are not probabilities. The probabilities of any specific value is 0, and a PDF can only be a PDF if the area under the graph is 1. Right? Those 3 things there are seriously important. So, how does this work with hybrid functions? Because they're back, ladies and gentlemen. Hybrid functions can be used to describe probability density functions. So, for example, we have a random variable x with a probability density function with that rule. Now, the minute I see in the question the words probability density function, I know that the area under that must equal 1. Or the integral of the function between 2 limits must equals 1. This question here says find the value of c, which makes the function a probability density function. At this moment in time, we don't know that that is, but we can constrain it. So, find the value of c. Well, I know that this section of my hybrid function is defined between 0 and 2. I'll explain this bit in a little bit. So what I now know is that the integral between 0 and 2 of cx dx must be equal 1. The area under that function, for it to be a PDF, must equals 1. How do I now go about doing this? Well, I just solve it. So c is a constant. Now I should be doing this underneath. So c is a constant, which becomes integral at 0 and 2 of x dx is equal to 1. Moving it over here so I've got some space, that would suggest that c square brackets of x squared on 2 between 2 and 0 must equal 1. Substitute in the values of 2 and 0. Well, when I put 0 in, so let's just do it anyway. c, I'm going to put in there, so 2 squared on 2 minus 0 squared on 2 is equal to 1. Well, that's 0. That's going to just give me 2. So 2c is equal to 1. And so my value of c is a half. So for this to be a probability density function, that value of c must be a half. Woo! Whoop, whoop. So what is this bit here all about? Well, I'm going to do a little bit of a side. So if we now know my function of x is defined by what did it say? C of x. So a half of x between 0 and 2. And it's going to include 2. And then I'm going to write that notation. This notation here can be written in a different way. And actually it can be written as 0 elsewhere. And I'm going to write 0 elsewhere. If you think about this function here, it's actually defined for all values of x. So here is my values of x, and here are my values of the function of x. It's defined for all of those values. Now, what does my graph of a half x look like? Well, it's going to actually go something like that. So here's my graph of a half x, and it's going to go to infinity and beyond. But the question is stating it's actually only valid between the values of 0 and 2. So here's my value of 0 and here is my value of 2. So what actually happens to the rest of this graph? Well, firstly, it doesn't exist outside of there. Just going to draw my axis back in. It doesn't exist, but we have to show, if you are ever asked in a question to draw these things, you have to do the following. So changing my pen color, I now have to draw a line, on that line that actually states that the values for all other values of x are 0. Now that's really hard to do in an exam. And by the way, if you are over here in Australia, do not do the coloring in thing, all right? Do it in a different color and do it slightly on and above the line so the examiner can see that you know that you've drawn that in there. Why do we need to do this? Well, because we are saying that the areas from minus infinity to infinity all add to make 1 for it to be a probability density function. So we have to put those lines on to say to the examiner, hey guys, we know that actually there is no area either side of 0 and 2. All right, back to the question, staying in the red pen. Having now got that information, it says find the probability that x is greater than 1.5. Well, for it to be greater than 1.5, if we're trying to find a probability, we're going to integrate. And we have to integrate our function, which in this situation now becomes a half of x dx. But what are my limits? Well, it's got to be greater than 1.5, so my lower limit is 1.5. And the highest limit of my graph, if you remember, is the value of 2. So I now integrate between 1.5 and 2 over half x dx. Now, doing this by hand, we do half is outside, and that's going to become x squared on 2, again, between the values of 2 and 1.5, which gives me a half. Substitute that in, let's not put the square brackets, but the curvy brackets, so we get 2 squared on 2 minus 1.5 squared on 2. So loading up my trusty calculator, let's put all of this in. 0.5, open brackets, 2 squared divided by 2 is 2, minus 1.5 divided by 2, all squared. Let's make sure we put that all squared so that my calculator doesn't get confused. All squared, close brackets, hit enter. And there we go, ladies and gentlemen. My probability that x is greater than 1.5 is 0.718, and we'll put 8 to 4 decimal places. Now again, the question didn't state to the limit of accuracy. I'm fairly sure it didn't. No, it didn't. So I'm going to leave it to 4 decimal places. Now we can have unbounded domains. Now what does it mean by an unbounded domain? It means that we can have an infinity. It can go on to infinity and beyond again, particularly with exponential graphs. Now if you haven't done exponentials yet, don't worry about it. It's a freaking awesome subject. But does it change anything? No, not really. So long as this is a probability density function, we know that this actually will have an area underneath that function of 1. So, firing up my calculator, opening my keyboard, and in here I have my integration sign under math 2. So, I want to integrate between infinity, I happen to have an infinity sign, and 0 of my function. So, what's my function? 2 times e to the power of negative 2x, and I want to do that dx. Hit enter, and lo and behold, what comes out my calculator? 1. So what that's now done is actually proven that I have an area of 1 under my graph. Awesome, loving the CAS calculator. Now as I say here, the CAS can do all sorts of stuff for you, and all sorts of different ways. The particularly great one for Casio ClassPad, and I'm sure for the TI Nspire as well, is we can define functions. We can define hybrid functions. This is just amazing. So for example, here is my define. I've put into my calculator define. So let's clear all my display for the moment and bring up my calculator so you can see what I'm doing. Right, so where is my define function? I think it's under math 3. So I'm going to define f of x, and I'm going to say equals. Now, where is my hybrid function? It just so happens it's here. So if I hit that button, it actually sets up a hybrid function for me. So I can do 2 times, go back to maths 1, e to the minus 2x, and we need to say for what values that's actually defined for. So I'm going to say x is greater than 0, and then we're going to put here a 0, and we're going to put x is less than or equal to 0. Now, actually, you don't need to put that. The calculator is quite clever. If you just put 0 and leave that blank, it knows that it's defined for 0 elsewhere. So I'm going to hit enter, and it's going to say done. So, having defined my function, I now go into, let's see, my integration sign. So I want it to go between 0 and infinity, and I want my function of x dx, and I'm going to hit enter, and after about 2 or 3 seconds, boom, out comes the value of 1. So that's proof, and it's done that for my hybrid function, which is awesome. I can also get it go between 1.5. Don't know where that infinity sign just came from, but if I wanted to find the probability between 0 and 1.5, again, out comes my calculator of 0.9502. Get to know how your calculator works. It will save you hours of time. And over here in Australia, when you are when you're doing the VCAR exam, all the multiple choice questions are massively CAS enabled. They are there and much, much quicker if you know how to use your CAS. Right, that's it. This has been another long lesson on continuous random variables. We've looked at what a random variable is, probability density function, and I am done for today. Thank you so much for watching. Look, guys, if you are able to, I'm on Patreon at this moment in time, just launched, so if you can pop over there and give me any help, that would be awesome. Otherwise, hey, you want to subscribe, you're not already subscribing, there you go, hit that button, get out there and tell your friends about these videos and my channel. Otherwise, there's a video loading over there. Thanks very much for taking the time for watching. I look forward to seeing you next time. Have a good day.